Okay, so I'm back. It's actually a different day now. I needed a little break. This is kind of where we were. I was telling you about the production of polypropylene and polyethylene. And it's particularly important right now that we not only produce polypropylene but process it into the desired form. Polypropylene, one of its most important current uses is in the N95 masks or even in other masks. It turns out that virus particles and particles in general can be attracted to fibers in polypropylene. They're often treated with charges, so they're often given a coating or otherwise treated to make them carry a charge, and virus particles and other particles adhere to them, and that's an important part of how they work. Well, maybe we'll talk about that a little bit in one of the synchronous sessions. Let's see. I think I ended by saying that it was kind of nice for people who live down the Gulf Coast. When there's not a hurricane, it's kind of a neat place. A little bit warm and humid. My student who moved down there to Dow Chemical said he's in an altogether different level of humidity than you have in Atlanta. And I can confirm the same is true of Baton Rouge. I always thought Houston was more humid than Baton Rouge, and this is a little south of Houston where those chemical plants are. But it is pretty. I had another friend who worked there. I visited that site many times. That guy, when he first moved down there, just bought himself a boat and lived right on the dock and sort of, rode a mile to work and then rode home and sat on his boat and took it out in the Gulf and went fishing. Good fishing out there, good seafood all along the Gulf. So it makes a certain amount of sense that people continue to live there, and we need these petrochemical production plants, at least for the foreseeable future we do. And kind of hopes that we find some alternative ways to recycle some of the existing product, but I'm sure we'll still be making product for a long time. It's now time to start telling you about polymers, and we're going to go by classifications of polymers first, because we kind of need to build a lexicon, a way to talk about them. We need to have some common ways to talk about polymers, and there's a certain language that goes with it, and you kind of have to know that, and so we'll start with that. And these yellow slides here will sort of demarcate different categories of polymers, and there's all sorts of different ways that you could classify the polymers. So this whole section is really about polymer classification. Linear polymers is the first thing that we'll mention, and linear polymers doesn't have enormous meaning. It just means that they have this shape here, and maybe each thing that I'm drawing here is a methylene group, So if we were to draw this, put in the hydrogens, it'd be this. Well, that's a countable number of carbons. 1, 2, 3, 4, 5, 6, 7, 8. That's just an octane. And if you put 100 of those together, then you would have a polymer. Okay. Or even if you put 20 of them together, you would begin to have something with the polymer. So this is, an octane. It's a liquid. If you make it long enough, it will. By the way, it's not all stretched out linear like that. It's not actually literally a line. This thing, if we made it longer, so now I don't know, I should have been counting how many I was putting in. It has bends because remember, if you had your organic chemistry, if you didn't, it's still true. Each of these carbons is a tetrahedron, and there is hydrogens there. That one shouldn't be there anymore. Well, we can put some on there. We'll say there's a branch point there. Good. Okay, so linear means that that it mostly goes in a straight line, and a real polyethylene or real polypropylene will have some of these branch points. We would still call that a mostly linear polymer. There are various amounts of branching that people put in. If you put in, I'm going to stop drawing all the individual methylene units now. I'm just going to draw it like this, okay? That's a truly linear polymer. If you put in stubby little things like this, okay, it's really starting to be a copolymer. And then at great expense and with enormously good technology in chemistry and catalysis, you can start putting in branch points like that. And this gives you a different property because it's difficult for the chains to pack next to each other in that branch zone. So anyway, a purely linear polymer has no branch points. No, we're not talking about copolymers with these little stubby things or anything. So we'll start with that, okay? But it does quickly get more complicated. All right, so the canonical polymer, the polymer that everybody likes to deal with in polymer physics, and the polymer that is enormously important in actual polymer chemistry itself, is polystyrene. And this is it here. This is polystyrene. And we usually just write PS for polystyrene. And it's a very easy thing to polymerize. Polystyrene, there's various chemical reactions that people use to make polymers, and polystyrene polymerizes with, I think, basically any of them. We can make this by, we make this by free radical. Polymerization. For polymerization, I just write PZN. It's much shorter. Free radical polymerization. We can make this by anionic PZN polymerization, cationic, there are various that's CRP. It doesn't stand for crap. It's controlled radical polymerization. So lots of different ways to make this. You can make this in an emulsion. And you'll be relieved we won't talk too very much about all of these. That's another course, and Georgia Tech has those courses for those who are interested. We have some upper level people in this class. We're not all sophomores. So some of you who are ready can think about taking the 4775 class. It's MSE, joint operated, MSE chemical and biological engineering, and I think chemistry may be on there too. I can't remember. Georgia Tech is really good about sharing these numbers. It's a brilliant system compared to my other universities. My good name. Anyway, it's the 4775 class. That's all you really need to know, and they'll teach you about these various polymerization mechanisms. And then there's even more advanced classes about, real polymerization that you can take. Well, this is a styrene monomer, okay? And it has a molecular weight of 104. I think we worked that out previously. And the chain has just exactly that same chemical formula, except at the end of it you might have I on one side. That doesn't mean I for iodine, that means I for initiator. And at the other end you have something else, put a star there. Something different can happen at the end, depends on how the chain forms. One option is to have another I with two chains that were going from one end join each other and make polystyrene I at the end, but that's just one option. There's lots of weird things that can happen there. But in any case, basically, except for these minor end effects, it's N repeat units of the styrene itself. And that's why this is called an addition polymer. It just adds the monomer units with almost no other change except at N groups. And N here is an integer, and let's see, the biggest one I know is 50 times 10 to the 6th, so we would have 50 times 10 to the 4th, or 5 times 10 to the 5th. Oops. I think N has to be less than about 5 times 10 to the 5th. So typically it's much smaller than that. Typical value of N might be 1,000. Okay, that's pretty easy to do. Well, that's one kind of polymer, and this is an example of an addition. Another kind of polymer is called a condensation. And condensation sounds like something that happens that gets wet, like water condenses on top of the surface. Well, if you were to add up all the atoms that you've got going on here, we have two different monomers. One is a diacid. If I wanted to, I could write this as two A's, right? And this is a dibase. Amino groups are basic. I could write that as BB. And if you were to add up all the atoms in that, you would find that it has made some water when it formed this. It gave off water. And so they say it condensed the water. Okay, fine. Doesn't really probably condense. There may be enough heat that it steams off or something. But anyway, it's called a condensation. And so here the product is chemically distinct from the two monomers. And that's not just an end effect. Okay, it's a major deal. There's a lot of change, a lot of water is given off. So let's, I guess we'll go back to that for a minute. I'll say these are old names. We'll talk about the new names in a little bit. So nobody should say addition and condensation anymore, but they do, trust me. It's ingrained into our culture. But there are more modern names for these two different kinds of processes. But the basic difference is in one, you have monomer that's just, the polymer is chemically the same as the monomer. And in the other, there's two different types of monomers, and you spit out some water as you go along. All right, so what we're going to try to do here, God help us, is to actually show how this goes. We'll try to put our knowledge of Lewis dot structures to use. Okay, so a typical initiator, I need to tell you what a typical initiator is here, would be something like benzoyl peroxide. You may know it as acne cream. Oops. Okay, and we could put in all the extra electrons if we wanted to have the full Lewis dot things. We could put them in here. Turns out that this bond here, this is a peroxide. This is the chemical benzoyl peroxide. Benzoyl peroxide and most peroxide have a weak bond. That OO bond in there is kind of like an uh-oh, it can fall apart type bond, okay? So this thing can split off into what's called a free radical. Okay, and I can't remember if I told you about the ring polymers. Why we draw the little ring. That kind of structure is equivalent to, but a lot faster to write, just to draw the little circle. Okay, so that gives us a radical, and we're going to call this just I dot, so I don't have to draw that all the time anymore. Well, free radicals are highly reactive species, and so they will go after anything they see. So what will happen in this case is that the free radical will find one of these styrenes to react with. And I really would like that not to be there. Let's get rid of that little thing. He's meaningless. Accidental dot. Okay. And it will attach to that, and you will get I. I'll actually remember this really has a carbon here with 2 hydrogens. This has over here a carbon with 1 hydrogen. So we'll write out what it actually makes. We'll put the atoms in this time. It makes a bond. Okay, it makes another free radical, is what it does. Okay, so the way this happens is that this, let's go back and put in all our atoms here so it's a little easier to see. Oops. Put in a C, H. Let's actually put those in. Okay, so remember that there's 4 dots in there in that double bond. A bond is 2 dots. And so what we really have there is some electrons, and so the free radical electron will actually go in and kind of attack there. Actually, I really want to just show that. Okay, and what it'll do is it kicks one of those, it forms a bond, a covalent bond, so we'll draw that with that one. and it leaves this one singly bonded. So there we have a single bond, and it kicks out that other electron, and now we have sort of like the first generation of polymer here. And so now I can write all that. I'll go a little bit faster here. This will find another one. And continue to grow. And the rest of it is one giant etc. Except that there are some things that can interfere. Just the simplest thing that might interfere is that two of these guys could join, okay? In which case you would get a termination by coupling. That will kill it. You would wind up with I, and I'm just going to write, those two radicals join together and stop the reaction. So that's termination by coupling. So it turns out that there's other ways for these chains, these polymer chains, to die. Well, the essential feature here is that whatever size chain you have at the moment only reacts with monomer. So it's always initiator plus monomer, or as soon as that happens, then you get chain plus monomer. So it's always that way. Only one thing at a time. Boy, sorry. Only one monomer at a time. All right, so that's a good place for a little break while we soak that in. Okay, I'm back. Short break. I'm going to switch to OneNote for these drawings because PowerPoint is just sort of unreliable on that apparently. I'm less familiar with OneNote, but let's give it a try. So the next thing we're going to do is condensation polymerization. We'll do a condensation pen. And our example there was nylon. And we'll try nylon 6,6, which means this one. And so I should fill in all the hydrogens here if I wanted to. You can see why people went to that stick structure, though it's just faster. I'll do something even faster now. So there should be 6 carbons there, and there should be 6 carbons here with amino groups on the other end. Hope that's right. It doesn't matter because there's various kinds of nylons you can make. And the basic reaction is what we'll see here. By the way, actual nylon is usually made by sort of a different type of process for high molecular weights, but this is an illustrative and possible doable type reaction. So it's just a lot easier if we draw this as, let's draw this way. Let's call that everything in there, the 4 carbons that are in there with their hydrogens attached, the 4 methylene groups. We'll just call that R, okay? And this one we'll call R prime. It's just a lot easier to write it that way. And I did put those unpaired electrons up there, unshared electrons, lone pair electrons. I put those in for a reason. I'll put in more. So if you remember back what we said about electronegativity, we said that further to the right on the periodic table or up makes an atom more electronegative. And so this kind of group here, this is a carbonyl group. It's called carbonyl. And it puts a carbon at the, puts a carbon in the presence of 2 more electronegative elements. And to make matters worse, the carbon, although it has 8 electrons, you can count the bonds, 1, 2, 3, 4 bonds, so there's 8 electrons available to that carbon, so its octet is satisfied. But one of those bonds is a double bond, and in double bonds the electrons are held a little more distant. So this carbon is electron deficient, and actually people will actually sometimes write a partial positive charge on that carbon. Partial charge is sort of a ridiculous term, but it helps us think, and there's lots of ridiculous things that help us think about these tiny atoms and their molecules. So anyway, that is an electron deficient carbon, and what will happen is the protons on this amino group are going to go over here. Sorry, the electrons in the amino group, not the protons. The electrons on the amino group are going to go over here, and they're going to attack that because, you know, electrons seek positive charges, even partial positive charges. So what will happen is that this set of electrons, one of the electrons in there will get bumped up and we'll wind up with a I'll leave the left side in a simple notation now. Happens like that. So this is really negative. This is actually there's a negative charge, and a nitrogen connected to 4-thing bears a. I shouldn't write partial here. This is really negative. I should just write negative minus. Let's put the minus where it belongs on the right side. And this nitrogen bears a plus. So that's obviously a high energy state. Okay, this is a transition state between the final product. What's going to happen is one way or other. the electrons are going to kick back down here to reform that double bond. And that's going to actually kick those electrons over to that oxygen. And somehow or other, one of these protons is going to fall off and migrate over here. Okay. This is one way to think about it. So the net result of this is going to be HOOC R C double bond O. Plus we'll have a proton and a OH group, which I guess what they're going to do, they're going to form water, and that's why we call it a condensation polymerization. So if we wanted to just really simplify this reaction, we would write it as acid group, because this carboxylic acid, this is a carboxylic acid group up here. So there are two of them, so that's a diacid. So we've really taken AA and we've reacted it with BB to give ourselves A, B, and water. Okay. Well, there is a problem here. You may remember from freshman chemistry that all these things exist in equilibrium. And there's this thing called Le Chatelier's principle. So if I want to make that reaction happen, if I want to produce ABAB out of AA plus BB, I should somehow get rid of this. Okay? So that would drive the reaction. The next thing to notice about this, though, so far, it didn't really have an initiator. It usually has a catalyst. If we were to draw a map of this, you know, if we were to say AA plus BB and say this is our reaction coordinate here, and look at the energetics, this comes back to what we were talking about before. Actually, I don't really kind of like the way that came out. Let's try a little bit better. This is a thermodynamically favored thing, the formation of this bond here, this bond right there is an amide bond, and they're stable bonds. So this is a good thing. We generate entropy by getting rid of the water, so it's driven. And we could look at the energy of this, you know, through the reaction coordinate. So this all happens very quickly, you know, less than a nanosecond. Kaboom. But there is this this state where I have, you know, AA here plus BB, and here I have that weird sort of situation where I have those charges. So remember that this thing required a negative charge and this one required a plus charge in that transition state. So we go through that sort of a state there, and I guess what I'm saying is that this is this whole thing here. This intermediate step there, that's our transition state. Let's just put a star to indicate that step. So this is that transition state. So there are ways to catalyze this, and when you catalyze a reaction, to catalyze a reaction, if you catalyze this reaction, it has the same look but with a smaller energy of activation. Okay, so our energy of activation should be here. And now that's our energy of activation. Now we have a smaller energy of activation. To the peak. Okay. So once it's catalyzed, we have a smaller energy activation. We don't have to worry about that, but there is a fair amount of chemistry that goes into doing that. Okay, so that is one thing to note. We're just reacting acid and base. There's a catalysis there, but there is not really the catalyst does not get involved in the structure. It just helps us stabilize that transition state. And it doesn't really get involved in the structures. There's no real initiator for this guy, as we've done it. And what we've done, again, to summarize, we did AA plus BB to give ourselves AABB. But once we do that, what's to prevent another AA plus the AABB that we previously made from reacting to give us AABBAA. And why then not have another BB come along and extend this. Okay, and that's not the half of it. Now, there's nothing to prevent us from having one of the previous things that we've made, let's say this one, react with that one. So we could have one of the things that we made A, B, B, A, could react that with the EB, A, B, B, A, and you can see that you could make then so I have all these species that end in AA and A, and I have a whole other set of species that end in B's. I could take this guy and react him with that one and continue to make larger and larger polymers. So basically, this is anything goes chemistry. And it is difficult to make this controlled. And we have big ones reacting with little ones reacting with littler ones, big ones reacting with big ones. And it turns out, as a result, that we get a bunch of polymers of different sizes from this, okay? And that was actually also true for the chain polymerization. So this thing is, and I have not been drawing the waters, as I'm just leaving all that out. But at every step here, there should be water given off, which is why we call it condensation. But what's really happening is that I'm letting everything react with everything. Whereas in the chain growth, we were adding monomers, a particular monomer, styrene, one at a time. So it's totally a different kind of thing, and it leads to different results. Okay, so we're back. I've cut and pasted the OneNote slides into my PowerPoint, so that's what you're looking at there. And I've added a little Opal logo. Opal is the Open Polymer Active Learning Laboratory. You could think of it like Invention Studio, but for people who want to learn polymers and use the very latest equipment, make a few polymers on your own. We have one girl who's very interested in making nylon by a reaction not so different than this. And then she wants to spin them all the way up into her own clothing. So that'll be cool. I hope it happens. And we think that you can do this even now. In small numbers, we think Opal has the safety to do it. It's a very safe place. It has enormously good air handling. So, the main point I wanted to make those is a kind of recap about this difference between addition, aka chain growth, and condensation, aka step growth. The difference is shown here with these little blocks. In addition, or chain growth polymerization, the chain always grows one monomer at a time. Okay? There's some sort of nasty termination reactions that happen. For example, this little yellow here could actually join with a little yellow there, and that would kill it. And then there's some other things that can happen that are weird. So in practice, it's not entirely simple. In condensation, the difference is that things of different size can be growing together. So in chain growth up here, it's always a monomer adding one at a time, okay, unless it's some crazy termination step that kills everything. But if it continues to grow, it's one monomer at a time. Whereas in condensation polymerization, you can have, what's this, a 6-mer hexamer with a trimer to make a nonomer, I guess. Then anyway, that could react with this, and that could react with that. You can get all sorts of stuff going on. So this is anything that reacts chemistry, and this is quite specific to growing one monomer at a time. It turns out that condensation polymers tend to be very low in molecular, not very low, but let's say it's very hard to get them to super high molecular weights. And that's important because molecular weight confers a lot of strength and viscosity and other things that we kind of want out of polymers as materials. So it can be achieved. You can get up to 50,000, and that's still a pretty substantial molecule. But for addition polymerizations, you can go much higher. And this is all about designing proper catalysts and doing the reactions under scrupulously clean and oxygen-free conditions. And then you can get to a molecular weight like 46 times 10 to the 6, 46 million. molecular weight. So that's pretty awesome. Okay, it's pretty high. And if you think about that from the standpoint of entropy, it's interesting because what you've done is you've taken all these monomers that were roaming around free, and now you've put them on this one polymer, this one chain. You've restricted them quite a lot. But you can still do it. We're used to seeing molecular weights of normal compounds, benzene, 78, water, 18, ammonia, 17 grams per mole. Now we're talking 50,000 or 46 million grams per mole, and grams hardly seems the right value anymore. I mean, it's still what we use, but it seems kind of silly. So you could actually convert this to tons per mole. I mean, these are, if you had a mole of this large polymer here, you would have many tons, several tons at least, of material, just because it's a big molecule. Now, nature is good at making step growth reactions. It makes them without the condensation in the normal sense, and it makes them quite precisely. But it's a much better chemical factory inside a living cell than anything mankind has developed. Okay, so summarizing some of the characteristics, an example of an addition is polystyrene. The canonical example of a condensation is nylon. There's no change from monomer in the empirical formula except for end effects. So if you ignore, the ends, it could be. And the bigger the chain gets, the less that matters. Changes as byproduct. Often it's water that's giving out. Doesn't have to be. Addition grows one monomer at a time. Condensation does whatever it wants. Polydispersity. You can get chains of different length. We really haven't talked about this yet. We're going to. This is, I should really define this term here while we have it though. So, polydispersity means same number of repeat units. Okay. These can be Paucidisperse. This means slightly deviating from the same. We're going to talk about this. Polydispersity here is what's called the most probable distribution. So this is okay, so we'll come back to that. Molecular weight can be very high for additions, pretty hard for condensations, except biopolymers can do it. And we've talked about the fact that this is two notations in existence now. Before we take another little break and I put this video up, I want to say just a few words about the process of making these reactions. It's easy to just go out there and put on a chemical equation, say, yeah, add an initiator to the styrene and wait a little while, you'll get this larger molecule. But actually doing it is a way in which you can have just an awful lot of choices. So there's what are called neat reaction. Doesn't mean neat as in, oh, cool, wow. It doesn't mean that. It means a neat, it means a simple fluid. So you just take styrene, for example, and heat it up and wait long enough and it will go into this solid. It will go from a monomer, which is a liquid in the case of styrene, into a solid, which is the polymer. You can also polymerize these chains in solvents, so you can dissolve the monomers in solvents. So you can do what are called microemulsions or emulsion polymerizations. You can do polymerizations in the gas phase. This is actually done by many tons per day. There's a reaction of the polymers inside an injection molding machine. So imagine that we're going to fill a mold with a shape. And as we're doing that, we're reacting it as it goes. And you can do that. There's another kind of novel thing called frontal boundary polymerization, which is really cool. If you had a material made of one of the right kinds of polymers, you just heat one side of it. It'll just sit there. It won't be reacting. It'll be like imagine a clay or something like that, something kind of solid-like. And then you touch one side of it with a soldering iron, something hot, and the whole thing just converts into a hard polymer. So this is frontal boundary polymerization. So there's various choices here that you can choose from. I want to say a little bit about this one, emulsion, microemulsion polymerization. So actually this is motivated by many reasons to motivate the existence of these frontal boundary, these emulsion polymerizations. But I hope you'll watch this YouTube. It's probably one of the earliest videos that you could think of, for a music video. And it's Martha Reeves and the Vandellas, and they're marching through. I don't know why they were doing this, but they're marching through this plant in 1965 where Mustangs are being made, the car Mustang. And trust me, we all wanted a Mustang in those days. Even someone such as myself, who's a Chrysler kind of guy, I really wanted a Mustang, but I didn't get it. I do now have the competitor to a Mustang. I have a Barracuda outside. But my uncle, turns out, my family is from Detroit, part of them. And we went up there and visited 1967. They were still making Mustangs, and for a long time they still make them now. But they don't look like this anymore. They still pretty much look like this, what you'll see if you watch this video. But the main thing to notice is this spray. This is a spray paint booth, and they're in there, these guys, they're painting. And they're painting Mustang hoods. I must be the primer because they're all the same coat, or maybe they just decided it was white hood day. And he's just spraying off in the distance, and I suppose there's a huge fan sucking the air up there. But it's still remarkable to me that they would let these three singers, Martha and her Vandellas, march through the paint booth and singing their song. I'm sure it was all staged. And nobody is wearing a mask. Nobody's wearing a mask. And paints in those days, well, first thing is they worked great. The paint that you get on a modern car is awful. I mean, you have to spend serious cash. You're talking upper-level Mercedes before that paint looks even semi-decent. Even Teslas don't look that amazing by comparison to what was just standard paint in those days, because they were all oil-based paints, lacquer and oil-based paints, and they're just so smooth because there's no surface tension. Well, we've switched now to different kinds of paint, latex-based paints, and now we don't have great gobs of benzene and toluene and methyl ethyl ketone and xylene going up into the hoods there and going out into the Detroit skyline and making a mess. So it's hugely important that we've made this switch to these latex-based materials that are made with these emulsions. Based polymerization. It's basically the same reaction I showed you, but it happens in a different way. So what you do is you have a monomer droplet. You have this droplet of monomer, so that might just be styrene. And styrene, here's styrene again. There's styrene. It's not going to dissolve in water. You can look at that and say, well, that's all carbon, it's all hydrocarbons, it's all oils. There's Hardly any polarity to that at all. It's not going to dissolve in water. But I can still pour some into water and just sit there unless I stir it. I could stir it like crazy. And if I stir it like crazy, I'll get these monomer droplets. And there's a lot of surface tension energy at the interface between the oily monomer phase and the aqueous phase. So this is watery, or we would say aqueous. And to minimize that surface tension, we put in molecules like this. We put in surfactants. So this is like basically soap. Okay, you just put in soap. Fine. Okay, these things that look like little Tootsie Roll Pops are soap molecules. And once you have the soap in there, then you can, some of the monomer droplets will break off, and in other ways you will form these smaller droplets called micelles. And they have relatively more surface area per unit volume, but still there's plenty of soap around to make that surface a little easier to create inside. So you really are able to mix oil and water if you add soap. It wouldn't work to clean your hands with soap if it wasn't true, okay? And then it starts polymerizing inside of this chain. So the monomer goes inside here. It's still monomer. And if you look carefully here, I don't know, it depends, but you can see that there's a chain in there growing. And there are really thousands of chains. And you have a problem on the current set about these kinds of polymers, particles. This is a particle. By the time it's done, it's a big particle. And here is an electron micrograph. It's an SEM image. Unfortunately, they didn't put a scale bar on it. I guess we could look in that publication, but I'm just going to make something up, okay? The idea of these particles, I don't know exactly how big these ones really are, but they're, probably, 0.2 microns. Maybe up to 1 micron, okay, in size. And you can see that you can make them quite uniform in size. It's super simple to do. I should put an opal symbol on here too. This is opal S. You can do this. You can make these. Just come see us in Opal and we'll let you make some. And then you can characterize them over at the mill on the SEM, and it's really cool. You might get something that looks quite like this. Actually, this is our first exposure, in a way, to what we'll see a lot of later on in this course. But look at here, we have some of them sort of packed in this sort of square array. This is a two-dimensional crystal here. It's to put these particles on a surface. And then if you look over here, let's see if I can find a good spot to draw this. This is good. You can imagine there's a hexagon in there. And we'll get a lot better at understanding these things when we get to other crystals. The hexagon can be made out of these two trapezoids, right? I have a trapezoid there. Let's see, we should have another trapezoid here. And I guess one here. So now we've made this hexagon. Okay, so you can make these particles uniform enough that they will form these structures. Of course, they're not as uniform as an atom of iron, a single atom of iron. All of those are the same, except some have different nuclei, maybe an extra neutron. Some of them will be missing an electron, who knows. But anyway, you can get these incredibly uniform particles, and they stack into these, they make these nice arrays. And you can actually use that. It turns out you can diffract light off of that. You can send in a light wave, and I don't know exactly which way to orient this light wave, so I don't read too much into the orientation here, but here's a light wave coming along. and it can actually just almost bounce off of this plane. Okay, so you can do optical diffraction. And so this, and it works out that it's of certain colors. It's only some colors that will do this. So if you aimed white light at it, you might reflect off only blue light. Or maybe it would only be green, or maybe it would only be red. So it kind of has an iridescent look to it. It's actually opalescent. So opals are an example, really. The opals that you buy in jewelry are an example of it, okay? This opal here is a make and measure space. It's like a maker space for people who also want to measure. And then we have, you know, real actual opals that are made out of particles like this. These are, you're going to calculate, in the problems that you work, you're going to calculate that there are a lot of chains in these things. And you're going to calculate that the overall mass of these little spheres, they're little, is still enormous compared to molecules. You know, any molecule you can think of. Still, these particles are massive compared to any molecule. And the overall structure is big enough that it can have function, okay? So you can add functions, use all sorts of things you can add to something like this. You can make them magnetic, and you can add chemicals to them that interact with other biomolecules. This is a big deal. This is a big deal. This is how a lot of biomarker testing is done, and this is how a lot of products are isolated. Okay. But there are other reasons for doing it. There are other reasons for making latex particles. One of them is that polymerization, if I just do neat polymerization, I just take styrene monomer and I heat it and get it to react, it gets pretty warm. It heats up, it liberates some heat when you make that reaction occur, because you're opening up a double bond, which is a high energy state, you're going to a lower energy state. It's exothermic. And how? And so if you're doing this on if you're doing it in a beaker, big deal, it's no problem, right? But if you're doing it in an industrial scale, and I showed you the scale of things, I showed you this reactor that's like 200 feet tall or something. And by the way, I've had the good fortune to look into one of those. It's really unnerving. I was actually able to go and look into one of those reactors about the size of what you saw. It was a different kind of reactor. And it's a little bit like staring into a thermos bottle, like you have that kind of lining bottle, and it's just like hard to have depth perception. All you can tell is it's huge in here. It's really big. Okay? But if you do something big like that, then the question is, how do you get the heat out of it? Okay? How do you get the heat out of it? So one of the main reasons we go to emulsion polymerizations, besides the reduced volatile compounds, we're making this stuff in water, for gosh sakes. So we're making a polymer, it's polystyrene, and we're winding up with these little beads that are dispersed in water. So now I can deliver the polymer, and instead of drawing off the volatile organic benzene, toluene, methyl ethyl ketone, and the rest, I just have water. It also means if I'm painting this stuff, I can clean up my paintbrush with water rather than turpentine or mineral spirits or something like that. Okay? So that's one reason. But the other reason is that the water can just absorb a lot of heat. Water has a high heat capacity, and we're going to put these oil drops in there, not in pure form. This monomer, oily monomer drops are going to be there, and they're going to be reacting inside these particles. But they'll be surrounded by water to take away the heat. Okay, so I want to push ahead a little bit forward at this point and talk about polydisperse, Paucidisperse, Monodisperse. Okay, and the first slide we're going to have on this shows those three situations. And what we're dealing with here This may not be so visible depending on the size of your screen. This is the number. The number of molecules with mass M. And when I say size here, I really should say mass. Usually, the size goes up with mass, so it's not a difference. But let's be specific about it and say mass. So let's say it is polystyrene. We know polystyrene, good old polystyrene. We just use the hell out of polystyrene. Okay, there's polystyrene. Has monomer molecular weight. It should be M1. I don't know why it's not M1, but anyway, it's M0. Okay? To 3 significant figures, it's 104 grams per mole. All right, let's. That means that everything that I see here is N times that mass, plus an initiator if I have an initiator. Let's just make up a number. Let's just say that this peak here is initiator plus 11. You know what? Let's let it be initiator plus 10. So this species that's in that part of the peak okay, initiator plus 10 styrenes. So you'd have to figure out what that is. You know, it's 10 times 104 plus whatever the initiator is. Make that a better one. Okay, so it's 1040 plus the molecular weight of initiator. Suppose we're using benzoyl peroxide as our initiator, so here's benzoyl peroxide. Okay, so what is this guy? We can figure this out. 1, 2, 3, 4, 5, 6, 7, C7. And then it has hydrogens here. H5 and O2. So that's 12 times 12, but we'll just do it roughly, okay? 7 times 12 is 84, and add 5 times 1 to make 89. And then I have 89 plus 32, which is 121, I guess. Okay, grams per mole. So this would be 1040 plus 121. So that's equal to 161. Okay, so that is the mass. Now, amazingly, so that's for this third peak here, it's supposed to be for this guy. Amazingly, we have a machine that can measure, can count. You can feed a sample of polymers into it, and it can tell you that you have, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, oh gosh, I lost track. 14. So I have 14 molecules in the sample have mass 1261 grams per mole. All right, and then I got nothing. Okay, I have nothing in between 1261 and the next one, which is going to be 1261 plus 104, which is what? 1365. So this next one here, if that first one is 1261, then this one is 1365. And I have more of them. I have 1, 2, 3, 4, 5, so I have 19 of those. Okay? So I can track out how many I have at a given mass. And the point is that they're not all the same in a polydisperse system. This is sort of typical. Okay? Polydisperse is typical. Monodisperse, if we're really good at our chemistry, super good, and for certain kinds of chemistry, and you'd never get it out of polystyrene, believe me, people have tried, you would have only one. All of them would be in just this one particular peak. Okay, and I don't know what that number is, but it's just one. And then you can have this thing called Paucidisperse. All right? So these are discrete distributions. Now one thing I need to have you understand is that most of the techniques that we can use to measure this do not have this ability to resolve one peak from the next, these little peaks, okay? They do not really have it. So this is the 1261 peak here, 1261. And that's the 1365. Most of the techniques we use do not resolve that well. And so what you get instead is something that looks like this. But whenever you see that smooth blue kind of curve, you have to remember underneath it really is that, because chemistry is nothing if not discrete, right? This is all the result of quantum mechanics. Chemistry is discrete. We can't have arbitrary masses in here. They're all going to be integers, integer numbers of the atoms involved. Okay, so there's polydisperse, monodisperse, and Paucidisperse. And here's a picture showing one of these things, a real one. This is an actual data, and this is a pretty small polymer, and that is a polystyrene, by the way. And that's actually, that is considered a Paucidisperse one. Really, this is actually pretty good. It's low molecular weight, but it's pretty good. All right, we have a formalism for doing this. Okay? So if I go back to that slide, and I say, okay, so I make a table here. I have, let's just say, M for 10, and it means 10 plus the initiator, right? We said that was 1261. And we said we had N of them is 14. And then we said M, when we went one more unit to get 1365, we added one more unit. That must be the 11 one, plus initiator. And we said that was 1365. I got to be careful with my units here, right? And that means that N, the number of these things, the number of 11 mers was 19. The number of 10 mers was 14. And for every one of these little spiky peaks, there's going to be a different M, which is always going to be something times 104 plus the initiator. And there's going to be a different N. All right? So let's see if we can generalize and come up with sort of a mathematical framework for this. Let M sub I equal let's call it Imer. Okay? So that's the mass of a chain that has I repeat units in it plus the initiator. And we can say let Ni be the number of Imers present. Okay? And we get away with some trickiness here. In principle, we could say let little n I be Ni divided by Avogadro's number. So it's a much smaller number. Okay? All right, let's see, I guess we can also Introduce Wi to be the mass of Imers present. This is fine. Okay, so, all right, so what you get depends on how you count. Okay, certain experimental variables connect to M sub n. Others of them connect to higher moments of the mass. So this Mn, let's deal with this one first. This is the number average weight. And I like to set this up like, let's suppose we wanted to get the average weight of a bunch of football players. We find, let's suppose that we have a really strange team, and we have, let's suppose we have a really strange team. Now it's gone crazy again on me. A strange team where we have we have 5 players at 170 pounds. Exactly all the same. Okay? Fine. It would never happen. And we had 7 players at 120 pounds. Okay, so this is junior high school, Pop Warner football, something like that. Okay, right? So if the average weight of the team, the average mass, M sub n, would be 170 plus 170 plus 170 plus 170 plus 170 plus 7 times 120 over the total number of players. So it would be 5 times 170 plus 7 times 120 over the total of 5 plus 7. So that's the simple mass that you would count if you counted democratically. You say every person counts on this team. I don't care if you weigh 5, if you weigh 170, you 5 that are 170, you are no more important than you 7 that are 120. That's exactly what you would count. You would get that number average mass. But it's football, okay? So depending on what your beliefs are, I happen to think that the offensive lineman might be the most important. And so we would weigh them more heavily. What if we wanted to factor into consideration the possibility that the more important is the offensive line? Okay? Because particularly in Pop Warner football, if you had a big offensive line, you could just mow down everybody, and then little lightweight kids could just sort of walk to the end zone unfettered by others. It's a strange football team with 12 players, by the way, but oh well, what the heck. All right, so if I wanted to count weight as a more important factor, I could take the weight of the players times the mass. Okay? So what I would do in that case is I would factor in their weight more heavily. Right? So I would take not the number of players, but the weight of players. Okay, well, how do I get the weight of the players? What is the weight of the players who weigh 170 pounds? Well, 5 times 170, which is what, 850, okay? So I would take 850 pounds of people who weigh 170, and then I would have 7 players at 120, so what's that? 7, that's 840. I would have 840 pounds of players who weigh 120. Okay, and then since weight is what matters, I would divide through by 850 plus 840. Okay, so that would be a different kind of average. Okay. That would be a different kind of average. And I guarantee you, this one is bigger. This weight average molecular mass is bigger than the number average mass. Okay? So, and what we really did to get our, we still have our 5 in here. It's just that we multiplied it by 170 to get this. Sorry. Yeah, we still have our 5. It's buried in this term here. This 850 is 5 times 170. So what's really going on in these weight averages is that you're taking the second moment of the mass. You're taking the number times the mass squared. So this is going to mess up your units totally unless you take the number times the mass in the denominator. Right? And it turns out that there are even higher moments that you can calculate. And we're out of analogy here, so we just call it Z. And this one works out to be the sum of Ni Mi cubed, and then to make the units work right, to come up with a mass. I wind up with that. Well, are we doing this just to torture you, or does it matter? No, it actually matters. Things like strength of a polymer correlate with that weight average molecular weight, right? When we're measuring these molecular weights, there are various experiments that you can do to measure them because you don't really know a priori what the degrees of polymerization. You don't know the distribution. You have to go in there and measure it. And so these measurement techniques respond to certain ones of them. Most of them respond to weight. One of them, it's very important, responds to number. but many of them respond to weight and mass. Okay, well, let's consider the case where every player weighed the same. On our football team, we have 12 players at, they're all identical. What happens if you have 12 players at 140? Just pick that randomly. If we put it into this formula, we can calculate MN, 12. Oh, I'm going to have to write this someplace else because, let's put it here, 12 players. Okay, so MN would be 12 times 140 over 12, which would be 140, so that's monodisperse, right? And MW, what would MW be? Well, MW would be 12 players times 140 squared. Divided by the total mass, which is 12 times 140, which would be 140. Okay? So when you only have one kind of player, then you have, uniformity. If you have uniformity, then MN is equal to MW. Anything else, MW will be greater than MN. Okay? And we used to have to, when we wrote our papers in journals, we used to have to type M, go get me a subscript, over M, go get me that subscript, and we would call this the PDI for Polydispersity Index. No more. We are now commanded by the powers that be. There are a certain number of people who have nothing better to do with their lives than to decide that we all have to start writing this D with a crazy bar through it, which does exist in your Windows font set. Trust me, it's there somewhere. And that is called not Polydispersity Index, it's just called, and not index at all, it's just called the dispersity. So you might say that this one is polymerically, politically correct. Okay, here's a picture that I showed you earlier in better form now. This is the high-res mass spectrum of a low-mass polystyrene. The peaks are separated by 104, as we mentioned, and that's what it looks like. There's a little bit of weirdness in this. This machine that catches this kind of data can actually measure individual molecules coming at it. So I don't exactly know what mass this is here. Goodness. Apparently. Really? Okay. Be that way. Just pick a mass here. One here, one of these peaks. Who cares what exactly it is? Okay. The machine actually counts. Let's suppose that this is a mass. It looks like it's 4,000, 5,000. It looks to be about 47, maybe 4,800 something. Who knows? Okay. It actually counted on the order of 350, 400, 375 molecules. Okay. It actually counts individual molecules. So it's not numbers like we were using earlier, which was like 11 and 17 or whatever it was. It's actually a large number of molecules. And again, it bears repeating that most instruments that we use do not have this kind of resolution, and what we normally see is that. Okay? And this is one from your book that shows the number average MN. the weight average MW being bigger than that, and the Z average being even bigger still. And then there's an example in your book. I'll let you study this on your own. You can just look at these slides. And what they've done here, they've thrown in the tau on having any kind of real resolution. They're taking, okay, so all the molecules in the range of 10,000 to 15,000, we have 0.16 of them. Well, that's nonsense. We don't have 0.16 of them. That's the fraction of them at 0.16, okay? So this 0.16, this represents N from 10,000 to 15,000 divided by the total. This is the mole fraction, for those of you who remember mole fraction from chemistry. Okay? And so they just let you build this average. And I'll just skip through that. You can watch that. And that's where I'm going to stop for now.